We start Module 2 with a simple concept, the transpose of a matrix, then move on to something a little bit more complex, that is, matrix multiplication. Taking a transpose of a matrix is an operation that involves changing the rows into columns and vice versa. Looking at the rows in our original matrix, we have our first row and our second row. They become the first column and the second column in the transpose of A. Another way of thinking about this is we switch the subscripts that indicate the element's position. So element Aij becomes element Aji in the transpose. Element 23, A23, becomes element A32 in A prime, the transpose. When we take the transpose of a transpose, we end up with the original matrix. If we multiply a matrix by a scalar, then take the transpose, it's the same as taking the transpose, then multiplying by the scalar. Let's work through some examples. Here we have three matrices, and we want to find the following transposes. The transpose of A 3 by 2, is the simplest case. As we saw before, we turn the rows in A into the columns in A prime. Now let's look at matrix C. We have C and the transpose of C, C prime. What we have here is that C prime is equal to C. C is a special type of matrix. If we consider the principal diagonal, we see that C is symmetric about that principal diagonal. In other words, our general element Aij is equal to Aji. So if we turn Aij into Aji, we end up with the original matrix. Symmetric matrices are square matrices. Here we have two matrices, A and B. They're both 3 by 2, so we can add them. And then we can take the transpose. Here we perform the addition, gives us this result, and we take the transpose, and we end up with a 2 by 3 matrix. Keep that solution in mind. Earlier we took the transpose of A. We can take the transpose of the transpose, and we see we end up with our original matrix. Back to matrices A and B. This time let's take the transpose of each and then add them. Here we have the transposes, then we add them, and so we see that A transpose plus B transpose is equal to the transpose of A plus B. Example 4 illustrates how, when we have equal matrices, the corresponding elements are equal. We use this fact to solve for U and V. Naturally, we start with the simplest case. We know that A13 is equal to B13. That implies U equals 3. We can check that. We have A11 is equal to B11. A11 is equal to 1 minus U squared. That's equal to 4. B11 is also equal to 4. Now let's solve for V. A23 is equal to B23. So we have 5 equal to U minus V. We know U already. Substituting in for U, we find that V equals minus 2. Now let's move on to matrix multiplication. The first thing we do before attempting matrix multiplication is to check that the matrices are compatible. That is, that they can in fact be multiplied. That means that the number of columns in the first matrix is equal to the number of rows in the second matrix. Remember, the order is important. The easiest and best way to check this is to write down the dimensions of each matrix. So in general, we'll have A as an n by n matrix and B an n by p matrix. To check whether the matrices are compatible, we look at the columns in the first matrix and the rows in the second matrix and see that they're equal. When we write down the dimensions, we have to have an equality between those two inner numbers. If A and B are compatible, then we end up with an m by p matrix as the result. Here's an example. If we have A as a 2 by 3 and B as a 3 by 4, the columns of the first are equal to the rows in the second, and C, the product, is a 2 by 4. If we try to multiply A and B in the reverse order, B times A, we see that they're not compatible. There's no solution. In general, the commutative rule doesn't apply to matrix multiplication. Of course, if A and B are square matrices, then we'll have both A times B and B times A, but they won't be equal. So, having set out when matrix multiplication can take place, let's now see how it's done. We'll start with 2 by 2 matrices. When we're multiplying matrices together, we need to think about the rows in the first matrix and the columns in the second matrix. To get element 1, 1 in the product, we multiply row 1 by column 1. To get element 1, 2, we multiply row 1 by column 2, etc. How do we multiply rows by columns? We multiply the corresponding elements and then sum up the products. So here we have 1, 1, row 1 by column 1. We have the first element in row 1 times the first element in column 1, A times E, and then the second element in row 1 times the second element in column 1, B times G, and we add them up, and so on. We can state that more formally in the following way, where the general element of the product, Cij, is equal to the sum from r equals 1 to n of AIR times BRJ. And we can see that there. The element Cij is called the inner product. Let's look at some examples. So we have matrices A and B. First we'll multiply A by B and then B by A. So we're looking at the rows in the first times the columns in the second. So we have 2 times minus 2 plus minus 1 times 1. Gives us our first element there, 1, 1. First row, first column, and so on. First row, second column, 1, 2. We'll have, again, 2 times 0 plus minus 1 times 4. 2 times 0 minus 1 times 4. Do those calculations, and we have our result. Similarly for B times A, rows in the first times columns in the second, and there we have the solution for B times A. Since B and A are square matrices, both A times B and B times A are compatible, but we see we have different results. We've seen that the commutative rule doesn't hold for matrix multiplication. The associative property does. Likewise, the distributive property. Recall that I is the identity matrix, so A times I is equal to I times A is equal to A. Here we have the null matrix. So A times the null matrix is equal to the null matrix times A is equal to the null matrix. Here's something that may not be intuitive. The transpose of A times B is equal to B transpose times A transpose. So we should remember that A times B is not equal to B times A in matrix multiplication. Also, if we have the product A times B that's equal to the null matrix, it doesn't necessarily apply that either A or B is equal to the null matrix. If we have A times B is equal to A times C, and A is not a null matrix, then it doesn't imply that B is equal to C. We'll see that in this example. We have matrices A and B, and we want to compute A times B. Rows in the first by columns in the second. We get the null matrix, even though neither A nor B is equal to a null matrix. So we have A times B is equal to the null matrix. We can let C equal the null matrix. So if we multiply A times C, we get a null matrix. That implies that A times B is equal to A times C, but B is not equal to C. We'll finish the module by identifying some special matrices. So if we have a square matrix A, we can square it, so we have A times A is equal to A squared. a squared times a is equal to a cubed, etc. If you square a, you'll get this result. I'll leave that to you. Sometimes we'll have a case for a square matrix where a squared is equal to a, and of course then a cubed is also equal to a. In that case, the square matrix A is an idempotent matrix. We've seen the case of a square matrix that is symmetric. The elements are symmetric around the principal diagonal. So in general, element aij is equal to aji, and the transpose of A is equal to A. The final case is for an orthogonal matrix. Here we have a square matrix where A transpose times A is equal to the identity matrix.